Okay, so in the next part of our discussion of solutions, we are going to talk about what are known as electrolytes. And there are essentially three different types of electrolytes that you come across. It turns out that solutions that contain ions are able to conduct electricity. Now, depending on the extent to which you have ions that are present, sort of dictates how much electricity that solution is able to conduct. But essentially, if you have ions generated in a solution, that solution is going to have the capability to conduct electricity. So in essence, we take a look at different solutes and their ability to produce ions in solution, either a great multitude, a little, or none at all. And essentially that gives us three different types of electrolytes. The first type of electrolyte that we come across are what are known as strong electrolytes. What defines a strong electrolyte is that strong electrolytes dissociate 100% in solution and exist only as ions in solution. So in other words, there's no more whole molecules that are present. You have essentially whole molecules, you have no more whole molecules present in solution. All you have left are essentially ions. Now, let's focus on this word dissociate. Dissociate essentially refers to the separation into ions, and essentially dissolve and dissociate do not mean the same thing. Because just because a substance dissolves does not mean that the substance dissociates. Just because a substance dissolves does not mean that the substance dissociates. All right, let's clean up a little bit of the writing a little bit here. Apologize for that. Because there are some substances that dissolve into solution and they will separate into ions, either totally or partially. And therefore, not only did that substance dissolve, but that substance also dissociated. But there are other substances that will dissolve into solution, but will remain totally as whole molecules upon doing so. And therefore, that substance dissolved, but it did not dissociate. Okay? So dissolve and dissociate technically do not mean the same thing. For a strong electrolyte, not only do you have to be able to dissociate, not only do you have to be able to separate into ions, but that dissociation has to be complete. No more whole molecules are going to exist. When that occurs, they form solutions that conduct an electric current strong enough to light a light bulb. So they're showing you an example here in the picture where they've hooked up electrodes to a light bulb plugged into an outlet. And what they're doing here is they're putting it into a sodium chloride solution. And you can see how the light bulb is lit up very brightly, because your strong electrolytes are excellent conductors of electricity. One other thing to mention before we look at an example is that all ionic compounds are strong electrolytes. And the reason why we mention this is that because if you look at aqueous solutions, there are a lot of ionic compounds that dissolve very readily into aqueous solutions. But there are some ionic compounds that only dissolve a little bit into aqueous solutions. Whether they dissolve a whole heck of a lot or only a little bit, once they dissolve in water, and that's what we're talking about aqueous solutions, their dissociation is going to be complete. So essentially, all ionic compounds, whether they dissolve a lot in water or only a little in water, they are considered strong electrolytes. So how can we tell from an equation that we're looking at a strong electrolyte? Well, on the bottom here, here's the equation for what happens when you take sodium chloride and you place it in water. First off, how do I know dissociation has taken place? I know that dissociation has taken place because the products are ions. Take NaCl solid, place it in water, the products are ions, Na plus, Cl minus. But what from that equation also tells me that the dissociation is complete? What tells me that the dissociation is complete is the fact that I have a single arrow. The single arrow tells me that when I take sodium chloride and place it in water, all the sodium chloride solid breaks apart into Na plus and Cl minus. It's a one-way street. All the reactant has been converted into product, and none of the product is recombining to form the reactant. So I know that dissociation has taken place because my products are ions, but the single arrow also tells me that my dissociation is complete. So NaCl in water, NaCl behaves as a strong electrolyte. Okay. Next, we have weak electrolytes. So what defines a weak electrolyte is that a weak electrolyte dissociates only slightly in solution. And because of that, they form a solution with a few ions, but mostly undissociated or whole molecules. So now, for a weak electrolyte, the dissociation is not complete. The dissociation is only partial. Now, you are able to conduct some electricity because you get some ions that are generated, but instead of being really excellent conductors of electricity, your weak electrolytes are poor conductors of electricity because there's only a minimal amount of ions that are present. So that's why if you look at the picture here on the slide, in this case, the electrodes of the light hooked up to the light bulb plugged into the outlet are being dipped into an HF solution. Notice how the light bulb is lit up, but it's lit up only dimly. Look at the comparison from the previous slide. That light bulb would light up the entire room. This light bulb would just generates a little bit of light. Why? Because there are some ions present, but not a whole heck of a lot of them. Okay. So weak electrolytes only partially dissociate in solution and exist as ions, probably only a few of them, and mostly undissociated whole molecules. So let's take a look at the equation for HF in water. So we take HF and we place it in water. Notice the two products, H plus and F minus. So the products are ions. So that tells us that some dissociation has taken place. But what from this equation tells us that in this case, the dissociation that takes place is only partial and not complete? In this case, it's the fact that we have double arrows. Now we have the back and the forth, reactant to product, product to reactant. So as soon as some of the HF dissociates into H plus and F minus, it's going to recombine. Not all of it, but a good chunk of it's going to recombine into HF, into HF. So at no point has all the HF become dissociated. In fact, probably only a little of it has become dissociated. And even though we have ions in the products, which means that dissociation has taken place, the double arrow tells us that this is absolutely partial dissociation. And therefore, HF in water behaves as a weak electrolyte. And then finally, you have your non-electrolytes. Now, non-electrolytes essentially do not dissociate. Okay, so let's see what's going on. Where non-electrolytes essentially do not dissociate. In solution. And essentially, they dissolve as molecules in solution and do not produce ions. So in solution, they exist only as molecules. No ions are present. And therefore, since no ions are being generated when that substance dissolves into solution, that solution is not able to conduct electricity. Okay, so your non-electrolytes do not dissociate in solution. They do not produce ions in solution, and essentially they exist as molecules, whole molecules in solution. So on the right here, you have an example. Again, we have the electrodes hooked up to the light bulb, which is plugged into an outlet. And this time they're dipping them into aqueous sucrose solution. And notice here that the light bulb is not lit up at all. Why is that the case? Well, on the bottom here, let's take a look at the equation for what happens when you take sucrose and you place it in water. In this equation, what tells us that dissolving in water has taken place is the change in state of sucrose from the solid form into aqueous. So that tells us that the sucrose, which started out as solid, after we placed it in water, now has an aqueous form, which tells us that it dissolved in water. But if you look at the product side here, what you notice is that there are no ions present. The sucrose whole molecules have remained as sucrose whole molecules. They're just in a different physical state. Instead of being a solid, they're dissolved in water. But because no ions are present, sucrose in water would not be able to conduct electricity. And therefore, sucrose in water would behave as a non-electrolyte. So one of the things you should be able to do is to look at an equation for a solute being dissolved in a solvent and be able to tell whether it's behaving as a strong electrolyte, a weak electrolyte, or a non-electrolyte. You don't have to memorize what is what, but you should be able to tell what's going on from looking at an equation.